So chapter 8. So every lab report that we do, I make you guys identify something that if you don't put it on your lab report, it's going to cost you 5 points. What is that? The experimental error, right? Because with every experiment, there are generally multiple places that experimental error can occur. And so I ask you to think about it, like what's the place that it was most likely to occur for this particular experiment, right? So there's some things that, since every experiment is going to have experimental error, there's some things that we can do to help minimize that. So a couple of things, 2 things to help minimize experimental error that we can do. Number 1, we can repeat the experiment. Repeat it multiple times. And take an average. We can do the experiment, and let's say in the experiment we get, this many grams of a particular substance. Experimental error can cause that value to vary. So to get a more accurate version of that, we do the experiment multiple times, take the mass at the end, and then we take the average of all the masses to guess what the most accurate value of that mass would be, right? So that's one thing that we can do to help minimize experimental error. Another thing that we can do is we can have others do the experiment. Because if we have others do the experiment, they may uncover mistakes you made. If you have someone else do the experiment you performed, then maybe you were making a mistake every time that you did it. And so having another set of eyes, another set of hands that are trying to do the experiment might reveal something that you did wrong. The good example of this was the steel wool experiment that I'll let you guys do for extra credit. I was never able to get sparks at the house. I don't know why. My tester said it was fully charged, and I tried it on a couple of different types of steel wool. I made sure it was just plain steel wool with no detergent on it. I still am not sure why I never got any sparks, but I never did. But several of you did the experiment and you were able to get sparks. So I would have probably thrown that experiment away and said it just doesn't work. But since it worked for several other people, I'm assuming it was experimental error on my part. So I'm going to have to go back and try that again. Maybe with a stronger battery. Maybe my battery tester was inaccurate. But so those are a couple of things that we can do to minimize experimental error. But because we're always having to deal with experimental error, we don't usually produce in our experiments the amount of a substance that our stoichiometric calculations are telling us that we should, right? We do these equations, and the equations are very precise and exact, and this is what you expect to happen. But like in the example where I said you get a certain mass of product at the end, often the mass of that product will not be what stoichiometry says that it should be, right? And so we need to talk about a term called percent yield. And so percent yield is defined as the actual yield divided by the theoretical yield. Whoops, that. In other words, the yield that our stoichiometry is telling us that we should get times 100%, because it'll give us a percentage. So like in the case of the mass of a particular product, we get a mass at the end, which is our actual yield, but then when we do the calculation based on the equation, we have a theoretical yield that we expect. So we divide that actual yield by the theoretical yield and multiply that times 100, and that's our percent yield. Usually the percentage is less than 100%. If it's greater, it probably means that some of what you think is product isn't product. So you're really not taken the mass of what was solely the product. Something else got introduced in there that you didn't realize was there. So any questions about the definition of percent yield? We're gonna do an example to use that equation. So it says on page 231, example 8.1, a chemist makes hydrogen gas according to the following chemical equations. They give us a chemical equation, put it at the top here. Our chemical equation says that we have zinc, solid form, plus 2HCl in aqueous form, yields ZnCl2, also aqueous, plus H2 as a gas. And it says the chemist uses an excess of zinc and 150 grams of HCl. So we have 150 grams of this. And when she collects the hydrogen gas, she finds she made 3.9 grams of this. What is her percent yield? Percent yield. All right, so how do we tackle this problem? Well, we already know, we just did it in our quiz, right? And I reviewed that with you. We already know how to go from grams of one substance to grams, yes?
So what does the AQ in parentheses mean?
It means aqueous, so it means it's been dissolved in water. Okay? So it'll be liquid in the experiment, but it's not just purely that substance. It's been dissolved. It's got water in it as well. So somehow I missed that because someone else asked me that actually on a test in the other class. So I thought I talked about aqueous in here before. Do you guys remember me talking about that?
I remember.
Yeah, maybe it was brief, but we mentioned it, but I guess I didn't stress it enough because you're not the only one to ask that question, Nathan. So anyway, we know how to go from grams of substance to grams of another substance. So we can go, we know we started with 150 grams of that. We measured that, right? And so we can figure out, based on this equation, how many grams of hydrogen we should produce. That's our theoretical yield, right? And then we take the value that we actually did produce, which was this 3.9, the actual yield, and we divide it by the theoretical yield and multiply it times 100% to get our value. All right, so the beginning of this problem is exactly what we just did on the quiz, right? Let's see how much H2 we should produce if we have 150 grams of hydrochloric acid. All right, let's start with that. So to go from 150 grams of hydrochloric, to go from grams of this to moles of this, we need to calculate what? The atomic mass. So for hydrochloric acid, HCl, the atomic mass is 1.01 plus, what's chlorine? Is that the 35.45? 35.45, so we get 36.46 AMU. So our first conversion relationship is that 1 mole of HCl is equal to 36.46 grams of HCl, right? So there's one conversion relationship. To go from moles of substance A to moles of substance B, we're going to go ahead and grab that value. So we know that 2 moles of HCl equals how many moles of H2?
1.
1 mole of H2. You understood 1 in the front of that. And then we'll just go ahead and calculate it because we know we're going to need it as well. What the atomic mass of H2 is. So H2 has an atomic mass of 2 times 1.01 or 2.02 AMU. So then we know that 1 mole of H2 is equal to 2.02 grams of H2. All right? So now we're going to do that big conversion so that we can get grams of H2. So we start off with 150 grams of HCl. We can convert that to moles of HCl. using this relationship. All right, grams of HCl cancel out, leaving us with moles of HCl. Then we can convert from moles of HCl to moles of H2 using that relationship. 1 mole, for every 1 mole of H2, we know we have 2 moles of HCl. So those will cancel out. We're left with moles of H2. Stop me if you're confused. If at some point you hit a wall and you're like, I don't know what you just did, let me know, okay? Again, all I'm doing here, I could do each of these things separately. I could say, okay, to convert from grams of HCl to moles of HCl, I do this. Grams of HCl times 1 mole of HCl over 36.46 grams of HCl. And I could calculate that out and get a number, and then I could do my next one. But I just think there's less room for error if you do it all together. Okay? So totally up to you, your preference. The last thing we've got to do is convert from moles of H2 to grams of H2, and so we're going to use this equation to do that. So 2.02 grams on top of H2 divided by 1 mole of H2, and sure enough, our units, moles of H2 cancel out. We're left with grams of H2, and so we punch all of that in our calculator, and we get a value of 4.16 grams. Now is that right? Yeah, 4.16 grams of H2. All right. So that is what value? In our percent yield equation, what value is that? That's the theoretical. That's what we expect to get, right? Like I said, normally you don't get what you expect, you get less. So this is what we expected to get. We know that percent yield is the actual value over the theoretical value, right? Times 100, times 100%. So actual was 3.9 grams. When we expected to get 4.16 grams times 100. So when we punch that in our calculator, we get 94% as our percent yield. Any questions at all about that? Did I start recording? Okay, I just panicked for a second. I was like, I don't remember hitting the record button. All right, if there are any questions, I'm going to move on. Going once. Going twice. Let's get closer, guys. You sure? No? Nothing to spell? No? Okay. Oh, it's too late. Sorry. I'm trying to wait. All right. We've done that several times. So that was, again, kind of practice for test 7. Again, right? So you guys have seen that a couple of times. Saw it when we went over it a couple of weeks ago. Like I said, do some more review problems if that's still confusing, because I want you to be ready for the test next week. All right, so let's talk about what we call the empirical formula of a substance. C6H12O6, that's glucose. It's a simple carbohydrate. A glucose molecule looks like that. It's got 6 carbon atoms, 12 hydrogen atoms, and 6 oxygen atoms bound together. Right? That's what the molecule actually looks like. And so that's what we call the molecular formula. A little more space in between there so you can see that's 2 words. That's the molecular formula because it shows, the molecular formula shows the actual number of each element in the compound. Really the actual number of atoms. Number of atoms of each element in the compound, right? The molecular formula tells us that. But we can also consider something that we call the empirical formula. And the empirical formula is the formula for the compound represented as the simplest ratio of elements. And so what that means is that if in your formula, if those subscripts that are in your formula that tell you how many of each atom you have, if they're all divisible by a common factor, then if you divide by that common factor, in this case every number is divisible by 6, right? So if we divide everything by 6, we end up getting this, CH2O. So that's actually the ratio of the elements in our compound, right? For every carbon atom, we have 2 hydrogen atoms, right? For every oxygen, we have 2 hydrogen atoms. And that's the same thing as you have up here. So this is the simplest form to write that so that you see just the ratio of elements, right? So this is called the empirical formula. Just to be clear, that is not what the molecule actually looks like, right? The molecule itself has 6 carbons, 12 hydrogens, and 6 oxygens. This formula just represents the ratio of those elements within the compound, okay? So the empirical formula gives the ratio of elements in a compound. All right, it tells us that there's twice as much hydrogen as there is carbon, twice as much hydrogen as there is oxygen. Sometimes the empirical formula and the molecular formula are the same, right? A water molecule is literally 2 hydrogen atoms and 1 oxygen atom. And there's the only common number you could divide these by would be 1, right? So you can't simplify that. That tells us the ratio. That's both our molecular formula and our empirical formula for water. So sometimes they're one and the same, but not always. Any questions about molecular and empirical formula? Okay. Let's see. I want to do an example, but I first want to show you a diagram on page, where is that? The drawing on page 234. So if you look on page 234 in your book, I just want you to see that ionic compounds, they always have the empirical formula for their chemical formulas. And that's because technically you see the ionic compound, which is what we refer to as table salt, NaCl, sodium chloride. It's just a bunch of ions connected together, right? Because they've got these electrical charges that hold it together. So you've got all of these single atoms that are bound together by the electrical charge. So for ionic compounds, the empirical formula will be the chemical formula, but not so for covalent compounds like water there. That's not always the case for the covalent compounds. All right, let's do an example, page 234, example 8.2. And so they ask the question, given this chemical formula, C8H12O4, is this an empirical or molecular formula? What's our test? Can it be divided by a common factor, right? And can this one?
Yes.
It can, right? So we say then that this is the molecular formula. Everybody see that? Everybody understand why that is? Okay. The next question is then, what is the empirical formula for this? What would it be?
C2H3O.
So we can divide everything by 4. That's the biggest number we can divide it all by. So C2H3O. Nathan's exactly right. I've forgotten to write people's names down. So Nathan, let's see, Jerry, no, Joey. Who are you? You don't, wait, there aren't pigtails today. That's what's messed me up. Doesn't someone always wear braids? No? You guys are messing with me, aren't you? Is it, I don't know. Is it Jerry? Okay, all right. Okay.
We sit in the same place.
I know, and it's
Sometimes
sad.
I should just be like,
It's
now
sad.
it's Joey.
The Metzger boys like always sit by one
Yeah,
another.
you
and
should
I'm-
tell them it's.
Always-
I should. I keep forgetting.
If you guys would just take a marker and write it on your forehead, I'd be good. Do you have a question, Cruz? Oh, no? Okay. Who else have I overlooked? I know other people have been answering questions. I heard you just say something a minute ago. All right, now. Here's the thing. I have a marker that's out of ink. So if I can ring this at the end of class, I'll just erase everybody's name and we'll just put +1 up there for everybody, right? But I want to tell you guys, sadly, I tried it a lot in the last class and I didn't ring it one time. It's because I didn't have your awesome placement back there, Austin. That's what we needed. So, okay. So this is the empirical formula. So the last question that they ask us here is related to a different compound. And I want to make sure you know how to do this. It says the empirical formula of a compound is CH5N. So they give us this for the empirical formula. That's the empirical. But they tell us that the molar mass for this compound is 93.21 grams. What is the molar mass? How do we find the molar mass of a compound? We just did it a bunch of times. We find the atomic mass, and then we say, if this is the atomic mass, then 1 mole of that compound equals this many grams, right? So that grams is what we call the molar mass. So we do that based on not the empirical formula, we do that based on the molecular formula, right? Molecular. So we use the molecular formula to figure out the molar mass, all right? So this is based on the molecular formula. So they want us to find out then what is the molecular formula. So how would we do that? Well, the way that we would do that is we would calculate the molar mass for the empirical formula. We figure out what the mass of 1 mole of this is. And then we would take the molecular formula's molar mass and we would divide it by whatever number we get here. And that's going to give us a ratio. And then we can take every number that's in here and multiply that by whatever that ratio is, and that'll give us what the molecular formula should be. So let's do that. So the first thing that we have to do is we have to calculate the molecular mass for this molecule. Now we know that's the empirical formula. That's not the molecular formula. But let's figure out the molar mass for that. So CH5N is going to be, what's carbon? 12.01. H is 1.01 and N is 14. So 12.01 plus 5 times 1.01 plus 14.01, right? So we add all that up and we get 31.07 AMU. And so that tells us that if we have 1 mole of CH5N, it's going to have a mass of 31.07 grams. And so again, this is the empirical formula, which is simpler than the molecular formula in most cases, right? Or in many cases. It is in this case anyway, because we see that it's not the same number. So since it's simpler, it's going to be smaller, right? So then we take this, oops, go the other way, sorry. Then we take the bigger number and divide it by the smaller, 31.07 grams, and that gives us a factor of 3.
How we figure out the empirical and molecular formula? Is it basically just the same as stoichiometry in the past, like we did?
Well, it's kind of, stoichiometry is based on the molecular formula, right, and the chemical equation. That's what stoichiometry is all about. This one, not so much. This is just,
Easier.
well, it's
Yes.
simpler because we're dealing with the empirical formula. But yeah, don't kind of put those together. The whole thing that we're doing here is we've got a simple, we're just looking at individual compounds, whereas stoichiometry is more about looking at the chemical equation, multiple compounds together, right? So what we're just trying to figure out here, can we determine, the whole point of this problem is that if I give you the empirical formula and also the molar mass for the molecular formula, you can figure out what the molecular formula is, okay? And we're going to see as we go on in the chapter why that's useful, all right? But the whole thing that we're taking away here is that we discovered, when we figured out the molar mass of the empirical formula, we discovered that it's three times this will give us the molar mass. And so what we want to do now to figure out, 3 times this will give us the molar mass of the molecular formula. So then what we want to do is take this 3 and multiply it by each of the subscripts on this. So the molecular formula then is going to be C 1 times 3, H 5 times 3, and then N 1 times 3. To give us a molecular formula of C3, H15, N3. So that's our molecular formula. Do you guys see how I did that? So I give you the empirical formula, which is not necessarily the... Tell me this. What if we had figured out, what if we knew the molar mass like we did here, and I gave you the empirical formula and you calculated the molar mass of this and it ended up being the same thing?
And it would also be, the molecular formula.
Then this would also be the molecular formula, right? It means that it's one of those substances where the molecular and the empirical formula are the same. But the process would still be the same, right? We get 1 here, and it would just say, well, multiply everything times 1, which is going to be the same number. So the process and how you figure that out is the same. But you won't ever get a bigger number here, right? Because this is the formula for the compound in simpler terms. It's going to have a lower mass because there's going to be either the same number of atoms or fewer atoms, right? So it'll always have a lower mass. All right, any questions about that before we move on to our last topic? All right, let's, so the basic way to do this, to convert from empirical to molecular, you have to know the molar mass, like they gave us. So then you divide that mass by the molar mass of the empirical formula, which is what we found here. We divided it and got a factor of 3, and then you multiply the empirical formula here by that factor. That's what we did down here. All right, the last thing that we want to talk about is finding the empirical formula of metal oxides. What are metal oxides? Those are substances that are formed whenever we burn metals. So when you burn something, you have to add what to it? What other compound are we adding to it? Oxygen, right? When we do a complete combustion equation, we do that substance plus O2, yields, in complete combustion, we get carbon dioxide and water, right? So metal oxides are produced whenever you burn metals, and so you're combining those metals with oxygen, right? So how do we get the empirical formula of metal oxides? There's 4 steps we can follow to get the empirical formulas for forms of metal oxides. Follow these steps. Number 1, measure the mass of the metal before burning and the mass of substance produced after burning. Oops. Not burning, burning. Are we going to expect that mass to be greater or smaller? We have a certain amount of metal, and we burn that metal, and it produces a different substance at the end. Do we expect the mass to be greater or less?
It'll be smaller because there's also carbon dioxide.
No, we're not. This isn't the complete combustion reaction. I was just reminding you guys when we do complete combustion, we're combining it with oxygen. But we're burning this metal to form a metal oxide. Yes?
Wouldn't it be the same?
Nope. It would be greater, and the reason why is because this metal oxide is the original metal combined now with oxygen, right? So since the oxygen has been combined to form this new compound, then the mass at the end is going to be greater than it was before. All right, that's what happens with metal oxides. Your metal combines with the oxygen to form a new compound. All right, so then after you do that, you take the after mass and subtract from it the before mass. And what is that going to equal based on what I just told you? Is it more massive at the end than it was at the beginning?
Oxygen.
Because oxygen's been added. So if you take the after mass and you subtract the before mass, you're going to get the mass of the oxygen. Right? Step number 3, use the molar mass. Use molar mass to calculate moles of metal and moles of oxygen. And by the way, use O, not O2 when you do this. So remember what we're trying to do. We're trying to figure out the empirical formula of metal oxides. So we're about to do an experiment where you take we're about to do a problem where you take zinc and you burn it, so you combine it with O2, O2, but what it's going to produce is zinc oxide. So we're trying to figure out the empirical formula for this. Right? And so in this equation here, if oxygen is combined with another substance to form a compound, it doesn't have to be O2 like it is if it's all by itself. Right? It's only when it's all by itself that it matters that it's a homonuclear diatomic. Right? Water is H2O. It's not H2O2. It can be a single oxygen atom if it's combined with another element. So that's why we're doing O and not O2. All right? I'll just leave that there. So we're trying to find the empirical formula. We're trying to find out the relationship between zinc and oxygen in this particular one here, in this example. And so last of all, we divide moles of metal by moles of oxygen to get ratio. To get the ratio of metal atoms to oxygen atoms. And so to do those steps, just so that it'll be a little clearer, we're going to do an actual example. And that's on page 236. So on page 236, we're told that a chemist burns 15 grams of zinc. Like I said, this is our equation. 15 grams of zinc. And the result is 18.7 grams of a white powder. We've got 18.7 grams of this. We don't know exactly what the ratio is. We don't know that this ratio is correct yet. But we do know that it's zinc and oxygen combined together, and we know that there's 18.7 grams of it. Okay? And so they ask us, what is the empirical formula of the product? So is this correct, or is it like ZN2O, or is it like ZNO2? What's the empirical formula? That's what they're asking us. So how do we figure that out? We go through these steps. Measure the mass of the metal, which they gave us, right? They told us it was 15 grams before burning, and measure the mass of the substance after burning, which they also gave us. They told us at the end we had a white powder that was 18.7 grams. And so from that, you can calculate the mass of oxygen by saying the final mass minus the original mass of the metal gives you the mass of oxygen, right? So we had 3.7 grams of oxygen that were in that white powder. We didn't lose any of our 15 grams of zinc because whatever mass you have at the beginning of the reaction of a particular element's got to be the same amount of that element you have at the end. The mass has got to stay the same. Law of mass conservation tells us that. All right, so we know we end up with 3.7 grams of oxygen. So that's step number 2. Now use the molar mass to calculate moles of metal and to calculate moles of oxygen. All right, so the molar mass of zinc, if we look that up, zinc has an atomic mass of 65.38. 65.38 AMU, that's the atomic mass. So that means that 1 mole of zinc is equal to 65.38 grams of zinc. So that's our molar mass right there, right? That's this, the molar mass of the metal. I'm sorry, the molar mass of the metal. That was right. I should have underlined that. That's the molar mass of the metal. But what we're trying to find out is the moles of the metal. So we can use this now to figure out the moles. If we started with 15 grams of our metal, 15 grams of zinc, how many moles is that? Well, it's 15 grams times 1 mole of zinc equals 65.38 grams of zinc. And so we do that calculation and we come up with 0.229 moles of zinc. Right? So that's the moles of metal right here. Now let's use the molar mass of oxygen to calculate the moles of oxygen that we have. And we know with oxygen that oxygen has an atomic mass of 16 AMU. So if we end up with 3.7 grams of oxygen, we multiply that, 1 mole of oxygen equals 16 grams of oxygen. And so we get 0.23 moles of oxygen. Should put zinc over there. So now we know that in our white powder, we have 0.229 moles of zinc, and we have 0.23 moles of oxygen. And so now we're on our last step. Divide the moles of the metal, 0.229, divided by the moles of oxygen, which is 0.23, to give us our ratio. And our ratio here is 1. In other words, for every 1 metal atom that we have 1 oxygen atom. So it turns out this is our empirical formula. It's ZnO. If we'd gotten a 2 here, then that would have meant that for every 2 zinc atoms, we have 1 oxygen atom. See how that works? That's our ratio.